I welcome you all to the course on fuzzy logic and neural networks. Now, in this particular course, we are trying to model human brain in the artificial way, and in other words, we are also going to discuss the principle of soft computing in details. Now, to start with the first topic, that is introduction to fuzzy sets. Now, here, so this is actually the topics which I am going to cover in this lecture. So, at first we will give a brief introduction to the classical set or the crisp set, and after that the properties of classical set or the crisp set will be discussed in details. Now, before I start with the concept of fuzzy sets, we will try to explain the reason behind going for this particular the fuzzy sets. We will also discuss how to represent a particular the fuzzy set. Now, introduction to the classical set or the crisp set, which is denoted by A. Now, before I just go for discussing like what do you mean by the fuzzy set, let me discuss what do you mean by classical set or the crisp set first. Now, to define the concept of the crisp set, so what we do is we try to explain the terms the universal set or universe of discourse. Now, let me take one example. Now, supposing that we are going to form a set of all technical universities in this world. Now, all the technical universities of this world will constitute one big set, and that is nothing but the universe of discourse or the universal set, that is denoted by capital X. Now, let me draw one universal set. Now, supposing that this is nothing but the universal set denoted by capital X. Now, next I am just going to ask another question, like can you not form a set of technical universities having at least 5 departments each? Now, if you just investigate a number of universities throughout the world will have at least 5 departments each, and there is a possibility that inside that universal set. So, I will be getting a subset, and this is nothing but this particular the subset, and this subset is nothing but the crisp set. So, this is nothing but the crisp set, because this set is having the well defined boundary. So, by definition the classical set or a crisp set, we mean a set with fixed and well defined the boundary. So, this is nothing but the classical set or the crisp set. The next I am just going to discuss how to represent a crisp set, that is denoted by A. Now, if you see the literature, the crisp set has been defined in 3 different ways. The first method, so A is nothing but a collection of all the elements like your A 1, A 2 up to A n. So, the classical set or the crisp set, this is written as A equals to a collection of A 1, A 2 up to A n. So, this is one way of representing the crisp set. The second method of representing the crisp set is as follows. So, A is nothing but a crisp set, which is nothing but x, the collection of x, such that it has got the property p x. So, p x is nothing but the property, and this particular symbol indicates such that. Now, so A is actually a crisp set which is having the properties p x, and this particular small x, of course, it belongs to your the universal set or universe of discourse. Now, The third method of representing the crisp set is as follows. We take the help of some characteristic function to represent the crisp set. Now, this mu a x represent the characteristic function of the crisp set A. Now, this mu a x is equals to 1 if x belongs to A, and if it does not belongs to A, then this mu a x is nothing but 0. Now, this is almost similar to the situation whether it is a member or a non-member. So, if it is member, then the characteristic function, that is mu a x is nothing but is equal to 1, and if it is a non-member, then the characteristic or the function that is equal to 0. So, this is either 1 or 0. So, these are the three ways actually we can represent the crisp set or the classical set. Now, let us see the sum of the properties of this particular crisp set, but before that let me try to concentrate on the notations which is generally used in set theory. Now, this set theory you have already studied, might be during your school days or in the first year of your undergraduation. So, whatever I am discussing related to the crisp set or the classical set, those are nothing but recapitulation for all of you. Now, this particular symbol, so this indicates actually the empty set or the null set. Then this symbol x belongs to A. So, x belongs to A. So, this is represented by this particular symbol. Then x does not belongs to A is this particular symbol. Then comes your A is a subset of B. So, this is the symbol which is generally used to represent A is a subset of B. The next is A is a superset of B. So, this is represented by this particular symbol, and if we write A is equals to B. So, this is the symbol, that means your set A is equal to set B, and if set A and set B are not equal, so you use this particular the symbol. So, these are the different symbols used, and there are a few other symbols also which we generally use in your the classical set or the crisp set. Now, here, so this particular symbol, so A is a proper subset of B. So, to represent A is a proper subset of B, so we use this particular symbol. Then the next symbol indicates A is a proper superset of B. So, this is nothing but A is a proper superset of B. Now, I am just going to concentrate on another symbol. So, this is actually the symbol, this is the symbol of the mod sign or the mod value. Now, this symbol indicates actually the cardinality of a set A, and by cardinality actually we mean the total number of elements present in a particular the set. Now, let me take a very simple example. Now, supposing that I have got the set, say this particular set, that is the crisp set, and it has got 3 elements like your A 1, A 2 and A 3. Now, what is the cardinality of this particular set? It is very simple. The cardinality of this particular set is nothing but 3, because it has got 3 elements A 1, A 2 and A 3. So, it is so simple. Now, the next symbol is P A. Now, this P A indicates power of set A. Now, by power of set A, we mean the maximum number of subsets that can be constructed from a particular the set. Now, let me try to concentrate on the same crisp set, that is A is a collection of 3 elements A 1, A 2, A 3. Now, let us see how many such subsets can be constructed from this particular set A, including the null. Now, if you see, So, if I take one element set that is called the singleton. So, I can from here I can construct the subset like A 1, next the subset like A 2, next I can construct A 3, next I can construct A 1 A 2, next I can construct A 2 A 3, next I can construct your A 3 A 1. I can also construct the same, that is your A 1 A 2 A 3, and I can also construct the null set. Now, let me count how many subset sets we have constructed. So, 1, 2, 3, 4, 5, 6, 7, 8. So, 8 such subsets I have constructed. Now, if I just try to find out what is the cardinality of this particular powered set of A, that means your what is this cardinality of powered set of A, and that is nothing but 8, because I am able to construct 8 such subsets. Now, this particular 8 can be written as 2 raised to the power 3, and that is nothing but 2 raised to the power cardinality of A. That means, your I can find out. So, this particular relationship, that is the cardinality of P A is nothing but 2 raised to the power cardinality of A. So, this is the way actually we can define the powered set of A and its cardinality. Now, I am just going to concentrate on some crisp set operations. Now, here I am just going to define like what do you mean by the difference between the two classical set, that is A minus B. Now, supposing that I have got one universal set or the universal discourse like this, and I have got two such classical set or the crisp set, one is nothing but A and another is nothing but B. So, my aim is to find out, so A minus B, that is the difference between A and B. Now, this A minus B is also known as the relative complement of set B with respect to set A, and mathematically, so A minus B is nothing but x such that x belongs to A and x does not belongs to B. Now, if you just follow that, so x belongs to A and x does not belongs to B, and there is one and in between. So, I will be getting, so A minus B is nothing but is your, so this black portion or the shaded portion, and that is nothing but the relative complement of B with respect to A. Now, let me take a very simple example. Now, supposing that I have got a classical set or a crisp set, that is nothing but A, and it has got a few elements like your A, B, C, D, E, say F. So, I have got say 6 elements. Now, I have got another classical set or the crisp set, so is denoted by B, and supposing that this is nothing but B, D, F. So, there are 3 elements. Now, if I find out, so this A minus B, how to find out the A minus B? It is very simple. So, I will be getting here A, then comes your C, and then I will be getting E. So, this is nothing but the difference between A and B or the relative complement of B with respect to A. Now, there is another concept that is called the absolute complement. So, this absolute complement, that is represented by A bar or A C. Now, here let us try to understand from here. So, supposing that we have got, so this is nothing but the universal set denoted by x, and I have got a crisp set that is denoted by A here. So, x minus A, that is nothing but the absolute complement of A, and this is nothing but your, so this your the black region or the shaded region. So, that is nothing but A C or the complement of your A. Now, this is the way actually we can define the concept of the difference between your the two fuzzy sets. Now, I am just going to discuss another, that is called the intersection between two crisp sets. Now, let me try to concentrate. So, this is nothing but X is nothing but my universal set or universe of discourse denoted by capital X. I have got two crisp set, one is called A and another is called B. So, by definition the intersection of A and B, that is A intersection B, is nothing but X such that X belongs to A and your X belongs to B. So, this is the common region between A and B, and if you see, so this particular black portion or the shaded portion is nothing but which is common to both A and B, and that indicates actually your A intersection B. Now, if I take the same example like say the crisp set which is having the elements like your A, B, C, D, E, F. So, I am taking the same example and supposing that I have got another crisp set and which is nothing but B, D, F. Now, if I try to find out the common region between A and B, and that is nothing but A intersection B, and that will be nothing but, so this should be common to both. So, this is nothing but is your B, D, F. So, this is what you mean by the intersection. And here let me mention, supposing that I have got two sets like set A and set B, and supposing that the two sets are disjoint. By disjoint we mean there is no common element between these two classical set or the crisp set. Now, if they are disjoint, so this particular A intersection B will be nothing but a null set. So, if A and B are disjoint, the intersection between these two sets are nothing but the null set. Now, these are all fundamentals of your the classical set, and all of us we know, and as I told, this is some sort of recapitulation. Now, then comes your the concept of the union. So, once again I have got the universal set, that is your capital X, and I have got two sets, two crisp set, one is called the A and another is nothing but your the B, and I am trying to find out the union, that is A union B, and that is nothing but X such that X belongs to A and there is or X belongs to B. That means, we consider the maximum area and this A union B. So, this particular the shaded portion or the black portion will be your A union B. Now, once again let me concentrate on the same example, like A is nothing but your A, B, C, D, E, F, and B is another crisp set which is nothing but is your B, D, F. Now, if I try to find out what should be A union B, it is very simple. So, we consider the maximum, that means your A union B will be nothing but A, B, C, D, E, F. So, this is nothing but is your A union B. So, this is the way actually we can define your the union of two crisp sets. Now, I am just going to concentrate on the properties of the crisp set, and these are very important because the crisp set follows all 10 laws. Now, I am just going to state the laws one after another, and as I told, this you people have already studied. So, this is some sort of recapitulation. The first law, now this is known as law of involution. So, it states that the complement of a crisp set is nothing but the original set. Okay. So, this is nothing but law of involution. The next is the law of commutativity. Now, it states that A union B is nothing but B union A, and another A intersection B is equal to B intersection A. So, this is nothing but law of commutativity. Next comes your law of associativity. It states that A union B union C is equal to A union B union C, and another statement like A intersection B intersection C is nothing but A intersection B intersection C. Now, then comes your law of distributivity. It states that A intersection B union C is nothing but your A intersection B union A intersection C, and there is another statement A union B intersection C is nothing but A union B intersection A union C. Next is your laws of tautology, that is A union A is nothing but A, and A intersection A is equal to A. Next come laws of absorption, which states that A union A intersection B is equal to A, and another statement A intersection A union B is nothing but A. Then comes laws of identity. A union X, X indicates actually the universal set, and that is equals to X. Then comes A intersection X is nothing but A union the null set is nothing but A, and A intersection null set is nothing but the null set. Now, then comes very famous De Morgan's laws. Now, it states that A intersection B complement of that is nothing but complement of A union complement of B. Another statement A union B complement is equal to A complement intersection B complement. So, these are very famous, as I told, De Morgan's laws. The next is your law of contradiction. Now, it states that A intersection A bar is nothing but the null set, and the last law, that is known as law of excluded middle, and it states that A union A bar, that is the complement, is nothing but the universal set. Now, here actually all such 10 rules are followed by the crisp set or the classical set. Now, then comes the concept of fuzzy set. Now, before I start with the concept of fuzzy set, let me try to spend some time just to understand why do you need the concept of this particular the fuzzy sets. Now, if you see the real world problems are very complex, very difficult, and these are associated with some sort of imprecisions and uncertainties. Now, prior to the year 1965, people used to believe that it is the probability theory which can tackle the different types of uncertainties in this particular the world. But in the year 1965, Professor L. Jade of the University of California, USA, he argued that there are many uncertainties in this particular world, and the probability theory can handle only one out of different uncertainties in this particular world, and there are a few uncertainties which cannot be tackled using the principle of probability theory, which works based on the classical set or the crisp set. And Professor Jade argued that we need something which is at higher level compared to the classical set if we want to represent the different types of uncertainties or the imprecision which we face in real world problems. Now, let me take a very simple example, very practical example. Now, supposing that one of your friends is going to market and you are requesting him, please bring 1 kg red apple for me. And supposing that your friend has brought that particular apple from the market, and there is a probability associated with the availability of apple, and it depends on the season. Now, there is an uncertainty of regarding the availability of the apple, and this particular uncertainty can be handled using the principle of probability theory, and the probability of getting apple varies from say 0 to 1, supposing that it is 0.6. So, with the probability 0.6, your friend has got some apples. Now, my next query is, what is the guarantee that this particular apple is red? How can you define the color red? And the definition of this particular color red will vary from person to person. Now, the problem is how to tackle this particular uncertainty regarding the guarantee that the color of the apple is red. So, this particular uncertainty cannot be answered using the probability theory or using the crisp set, and to answer that we need to have another set, and that is nothing but is the fuzzy sets. Now, the same example which I took, let me just write it here. Now, the color of this particular apple is red. Now, according to this classical set or the crisp set, there are only two possibilities. One is the apple will be red or it will not be red. So, there are two answers, one is yes and another is no. So, if the apple is found to be red, its characteristic value is 1.0, and if it is not, its characteristic value is 0.0. So, in classical set or the crisp set, so there are only two answers, one is the member, another is non-member, that means 1.0 and or 0.0. But the same color red, so that will be defined in a slightly different way in fuzzy sets. For example, the color red can be perfectly red, and the same color some other person may say this is almost red, AR. Some other person will say this is slightly red, and there could be a possibility that it may not be not red also. Okay. Now, if it is perfectly red, then we declare it is red with membership function value. So, I am just defining a term that is called the membership function value, and that is nothing but the degree of belongingness, and that is nothing but the similarity of an element to a particular the class. Now, this particular membership function value will vary from 0 to 1. Now, as I told, if it is perfectly red, then we say that it is red with membership function value 1.0. and if it is almost red, then also it is called red with say membership function value 0.8. If it is slightly red, then also it is called as red with membership function value 0.4, and if it is not red, then also it is red with membership function value 0.0. So, this is actually we define the color red in your the fuzzy sets, and now you can see. So, this particular fuzzy set is actually a very practical way of representing so this type of uncertainties, and that is why actually. So, this particular the fuzzy set has gained popularity. Thank you.